Good afternoon, everyone. Thanks for coming to class. I really appreciate it. Good evening. Sorry. I forget that our class starts at 6:30 in the evening. Um, with that said, I got a couple of announcements and um yeah, thank you guys for coming. My first announcement is that I really appreciate the responses that I got. It seems like a lot of folks, I think that I saw at least 45 people responded to the surveys. I really appreciate that because I on Friday, I started looking through the responses, and some of the short answer responses were it'd be helpful if you did a review of things because it's been a while since I've taken Gen Chem 1. And I apologize. I don't want you to think that I never want you to think that the attitude I have about this class is I am biochemistry's gatekeeper and you got to figure it out. That's not my approach. That's not what I want. In the event that I talk about something um and I don't give it adequate context, I apologize. And if you can either jot those things down um and send them to me. If it's something like acute, like I really need a refresher on this, I will do my best to respond to that and give something on the fly. Or if it's something like, hey, we talked about this a few days ago. I thought I had it, but I feel like I'm a little bit off. Please don't hesitate to contact me. Or just, wait until I'm going to do those surveys. My plan is to do them on a weekly basis, just so I can have a sense of, people's confidence levels. In addition to that, one of the consistent, so sorry, in addition to the, hey, I'd like more context, I got quite a few people who responded with, I feel like I'm okay, but I want to see how these questions or how you ask us on exams about this content. Sort of like, and I feel I understand that where it's like, hey, I feel all right about the quizzes, but are the quizzes the is that the rigor that you're going to be expecting or that we should expect on the exams? And so what I'm going to be doing and hopefully have by the end of this week is two things. I'm hoping to have kind of your learning objectives for exam one so that you can kind of begin your own study. Like if I were to explore this topic, these are the things that he wants me to know about. But also, I'm while I'm writing your exam one, I'm also writing a practice exam. So I'm hoping to have that practice exam up on Canvas on Friday. And I've done this before, and I thought it was kind of a good thing where I gave a practice exam and basically set the parameters just like I would on your actual exam. The only thing is I won't have like Proctorio enabled and you don't have to like it's not going to be proctored. But there will be the time constraints, 80 minutes. But the thing that will make it a little bit different is you'll have 999 times to attempt it. Um, so, that will be a good opportunity for you to like see the questions that I'm asking, see the rigor, the depth, like, and what I encourage you to do is, take it cold and be like, where am I? I'll make it so you can see the answers. Um, but then you'll also be able to see like, okay, I took this cold and I got a 65. Okay. The questions that I got right, how do I feel about those? I feel great about those. The questions that I got wrong, I narrowed it to two. So, based on the how the winds are blowing, I could have gotten, 65 was kind of the basement that I would get. I could get as high as an 85 or something. So that's kind of my rationale there. So those are two of the things that I saw in the survey results. And then I also saw lots of responses like, Zoom is kind of hard to stay awake during. Um, Kind of like and the tone that I got, the message that I got was like, it's not you, Joel. It's just like the nature of sitting at a computer can be a little bit disruptive. And so sort of sticky and hard to do. And so I've got some plans on how I can address that, both with like Zoom poll questions, but also like things that we can do during class to kind of like mix it up and hey, draw this. and then I'll kind of work alongside it. So, I still have to collect, I still have to like look through all of the data. Um, I would say most people were at a three, four, or a five in terms of their confidence level. For every individual, though, what matters to you is how you feel about it. I want to get everyone by test day. I want everyone to be at a five, and then the day after test, or right after you're taking your test, I want everyone to be like, feel like a four. I'm not trying to like bring you down, but I'm just like a test is always kind of a stressful time, and I'd rather you feel like a four than like I took a test and I'm at a one. So anyway, with that in mind, what we've been talking about. So okay, that was that. The quizzes for this week are up. You've got two activities. One of them is a crossword, so it's dealing with some of the jargon. But then the worksheet, or the activity that I have, if I remember correctly, is about amino acids. I'm also working on another worksheet that is going to be very comprehensive that I will have probably no later than Friday as well. Um, and so I will, so that worksheet is going to be like basically, whenever I say comprehensive, it's going to say, here are everything that you need to be able to do for all 20 amino acids. And so every question will be related to every single amino acid. Do you have to do that? No, you don't. It's going to be practice. I'm going to give you kind of model responses. Um, I got a private message. The course calendar and syllabus have conflicting test dates. Is the test on the 12th or the 19th? I have to look at the course calendar right now because the course calendar is correct. So, um, the exam, the first exam is on February 19th. So I will correct that in the syllabus. I'm going to write a note to myself, 4375. Sorry about that. I hope that everyone who, if you're taking your exam in the testing center, exam one is the 19th of Feb. You can, talk to me if you have an issue there. Okay, now, yeah, the quizzes and activities are up. I'm going to grade the activities, and then that's what we got. So, with that in mind, here's our PowerPoint. So, we've talked about amino acids. And one of the things that we most recently talked about was calculating the charge as well as the pi of an amino acid. And the charge and the pi, or the isoelectric point of a peptide. Now, one thing that I want to make sure everyone's familiar with is that an isoelectric point is a term that you've probably not heard until this class. And so that term pi might also be a little bit new. So if you're like, I don't remember learning about a pi, this is probably the first time that you've heard about it. This is where 100% of your molecule has a zero charge. Now, with that, um, I'm saying molecule. In this case, we're talking about a biological molecule. Um, could this be true of a like phosphate, or, is there a point whenever you get something like phosphate to have a zero charge? Sure. This is significant for biological molecules for the purposes of separating them. So in addition to this is where the 100% of the molecule has a zero charge, this is also where the molecule is least soluble. I'm going to grab the chat because I see someone added something. Yes, pi and isoelectric point are the same thing. So your pi, or your isoelectric point, same thing. 100% of your molecule has a zero charge. Now, this is really important because as biochemists and biologists, one of the things that you regularly do is you separate a protein from a complex mixture. And I think that um, some of y'all maybe have a little bit of experience with an insoluble protein. I'll give you a hint, and then I'd like somebody to add something to the chat. Now, this is not product placement or my abilities as a commercial model of sorts, but this is my hint as to what you might be familiar with as an insoluble protein. So milk, I like it, but here my product placement was too far. Protein shakes, absolutely whey protein. I'm guessing that some of you have maybe been like, "Ooh, yeah, and maybe you're a much more disciplined person than I am, but I'll share my experience, and I don't know if it's relatable to anyone, but it's like, I need to start lifting weights. So I got to go and I can get some whey protein. So I go and I get my whey protein, and then it's like, oh, the bottle says just add to water, and then you add to water, and you're like, all right, this is step one in the journey. It begins today, and then you pick up the glass, and you're like, this tastes like how the plastic container smells. But this is the journey. And you drink the first portion of it, and then at the bottom, what do you have? You have a bunch of an insoluble protein, and you're just like, I think that I don't think strength training is how I'm going to go. I think I will chicken breast. More chicken breast. That's what I need. If you like protein shakes, then you have figured out something more than I have, and that is how to like mix it up so that stuff stays in solution. My experience with whey protein is you add it to water and it's like half of it crashes out. And the point is, what I'm getting at with my unnecessarily elaborate story is that when that protein is insoluble, it stays as clumps. And so if I wanted to, let's say I had whey protein and some other protein, and well, I added water to it, and some of it precipitated out, it existed as the solid, well, then that would be close to its PI. Blend it with milk in a frozen bin. I, you're right. I know there are ways. I have now I go to Costco and I get this guy. This is these are decent enough for me. It stays in solution. But I've had the experience where I'm like, oh yeah, this stuff, and then it just like crashes out because that protein, there's a reason for it. That protein is in that water, it's near its PI, and so it's least soluble. And so if I wanted to, I could go to, Whole Foods or something and get one of those Essentia waters with a pH that's a little bit higher. That basic water, that alkaline water. If I mixed it with alkaline water, I probably wouldn't have the same experience because the pH of that water is a little bit higher. So that's a little bit farther from my whey protein's PI. So that's kind of that's like a connection between the chemical aspect of it and maybe what you've seen. And the shaker bottles also work because then it's just like you just keep shaking it, add a little bit of water, and it stays in solution a little bit better. So that's what PI is, where 100% of our molecule has a overall charge of zero. That means it has basically an equal number of positive and negative charges, so they effectively cancel one another out. Thank you very much. I appreciate that. I've got what do I have? I've got a Ninja blender and it does all right. I have seen the Ninja Cream Eye and that I've seen people on Instagram. It's like some guy who makes imitation ice cream, and I'm tempted by that. But I feel like what I would do is I would just add a bunch of Oreos to it and I'd be like, it's healthy ice cream. Because after all, Oreos are vegan. So, at any rate, what I'm showing on this slide, in addition to PI, is I'm showing a couple of different things. On the far left-hand side, we've got our dipeptide. We've seen this model before where it's the amino acids. We've got our N termini on the left, and we've got our C termini on the right. Then what we have in the middle here, I'm going to erase this right here. We've got our peptide bond. Our peptide bond is what connects the C termini of one amino acid to the N termini of the next amino acid. Now that is, and we're going to go into more detail on this in just a moment, but this is what is known as the primary structure of a protein. And maybe in some of your biology classes or another class, you've heard about the different levels of protein structure. You've heard about the primary, secondary, tertiary, and last but not least, quaternary structure. When we talk about the primary structure, this is it. This model on the far left. And arguably, this model in the middle is another representation of that. It's got a little bit more of a flow to it in that you can see the individual amino acid titles or the three-letter codes there. But all of that builds up to this right here, our model on the far right-hand side. Now, that model in particular on the far right-hand side is a single polypeptide, a single protein that has folded. And what's difficult to see in 2D is that there's some depth to this. So this is a three-dimensional model. So this has to do with this one on the far left, or far right, I'm sorry. We're looking at the Y plane, so the height of it, the X plane, the width of it, and then this last one, our Z plane, basically the depth of it. So when we talk about proteins and we talk about them, like what they do, we are interested in all three of those planes, the X, Y, and Z plane. We're interested in that depth. Now, with that in mind, these are our four levels. Our primary, which you will sometimes see me denote that with one and then this not symbol. Secondary, which gets the two and the not. Tertiary, three and not. And quaternary, four and not. So all of these different levels, they kind of have different levels of complexity. I have to confess, I like Super Nintendo. Um, and so what I sometimes do is I always kind of, or not, I sometimes always, I sometimes have a tendency to think about this as primary. Well, you get a little bit of information. This is like the NES, the regular Nintendo, the one from 1985 or whenever it was. And you know what? You saw Mario run from the left-hand side to the right-hand side of the screen. He'd jump and then he'd die. Or he'd be victorious. Then there's an evolution almost. The Super Nintendo system. And with the Super Nintendo, you got a little bit more depth. The graphics were a little bit more refined. You got a little bit more information about Mario and like what he looked like and everything like that. Then our tertiary, I'm going to go with the N64. And then our quaternary, I'm going to go with, I'll just go with the GameCube. So the point with all of these is that if you think about the different incarnations or the different iterations of Mario, you got a little bit more refinement as to what Mario looked like. And so this same sort of thing, we get these different refinements with proteins. If you know about the primary structure of a protein, GameCube is a hit. My old my friends in high school and then college would um yeah, they played monkey ball, super monkey ball a lot. Anyway, so with if you have the primary structure of a protein, you've got some information. You've got the sequence of it. And just as we've learned a little bit about the amino acid structures, we know there are some that are polar, some that are non-polar, and we've got a little bit of information. Can we, with just the primary structure, put together a complete story? Not yet. But what we can do is we can be like, oh, well, I see this 700 amino acid long protein, and I see there's a cluster there's a bunch of positively charged residues, and then there's a bunch of negatively charged residues. I wonder if those two sections of this polypeptide interact. I don't know. When you have the primary structure, that's a great question to ask. Next level, when you have secondary structure information, you have a little bit more information. you have a little bit more depth. You have a little bit more of an idea of, oh, okay, well, this part, so if we looked at a polypeptide, we'd say, oh, well, this part of the polypeptide right here is able to interact with this one right here. Oh, you know what? I think that that might rotate, that might fold into a particular shape. And then our tertiary and quaternary structures, at these points, you then to begin to really care about what are the amino acids? Like, what does every individual residue do? It's it's valid information at those higher levels, at those lower levels, the primary and secondary structure. It's valuable, but it's not really something that you can use at those levels because it's not completely relevant. And I hope that that will make a little bit more sense as we progress through these descriptions. So, the first level that I'd like to talk about and go into more depth is our primary structure. Now, that slide that we just showed, that I just showed you, the stabilizing force, those are going to be very important, and I'll get into those individually as we progress through them. Because what's important is to have an understanding of what the structure tells you, but then what stabilizes that structure. Okay, so our primary structure. We read our primary structure from the N termini to the C termini. Now, what stabilizes, just as we've got this model right here, what stabilizes our primary structure is, well, it's peptide bonds. Now, one thing that I want to clear up is that a peptide bond is an example of a covalent bond. And I'm going to go into bonding review in just a moment, in part because there are folks who asked for that. And I think that this is a very critical time to be thinking about like bonding and remembering bonding. Okay, so a peptide bond is an example of a covalent bond. So between this carbon right here and this nitrogen right here, we've got these electrons that are shared. Now, whenever we talk about the primary structure of a polypeptide or of a protein, if I say AKLRGS, I want you to, by the time the test rolls around, I want you to be kind of like muscle memory, recalling and reading something like this. Will you have an exam question that asks you explicitly, what's the sequence of this peptide? Probably. So the more comfortable you get with those single letter and three-letter codes, the better off. This is going to be an N-terminal alanine. And that's another way that I like to ask that sort of question, where I'll say, okay, well, here's your peptide. Which is the N-terminal amino acid? In which case, start on the left and go to the right. On the left, it's an alanine. It's an alanine followed by a lysine, followed by a leucine, arginine, glycine, and serine. Now that's kind of so that's that right there is a primary sequence. Now, typically you're going to see this as the single letter codes. From time to time, if you're dealing with a short peptide, something that's like 10 amino acids long, you might see that denoted by the three-letter code. So it might be like, and that almost just becomes like a marketing name of sorts, where it's just like, oh, well, this is the ala. Oh, I just came up with this one. Oh, the allylyser peptide. That's it's a very hot commodity on the market these days. And that statement alone is why you can look at this class and say, that person is not a business person. Because me just saying hot commodity on the marketplace is the limitation of my business knowledge. So three-letter codes are typically reserved for, shorter peptides. And examples, ARK, ALA, ARG, and LYS. That would be our translation from our one-letter and our three-letter codes. The primary structure is just your amino acid sequence. And this last item right here, a peptide or anything less than 50, sorry, is anything less than 50 amino acids. A protein is anything larger than that. Now, that's not like a hard and fast definition, but it's one thing to kind of keep in mind. I will con I will confess that from time to time I'll refer to a 750 amino acid long polypeptide. More accurately, that's a protein. But is it still a polypeptide? It is. But typically the definition is 50 and longer is a polypeptide, shorter than, or sorry, 50 or longer is a protein, shorter than that is your polypeptide. Okay, now is it a rectangle? I think that's probably fair to say. Yes, I think that's a fair assessment. A square is a rectangle's not a square. Because you're not going to talk about a 30 amino acid long protein. I love that example. Thank you for asking that. Okay, now a little bit about bonding, just to bring things back. If you feel good about bonding, take a little napper. You're good. Um, what we are interested in this class when it comes to bonding is we are mostly interested in your intermolecular forces. Um, we will talk about intramolecular forces as well, um, because whenever we have a peptide bond, we have a covalent bond there. When it comes to bonding, one thing that's really important is to think about valence electrons. And whenever I think about valence electrons, I have a tendency to think about electronegativity. And I think about electronegativity because I got to be honest with you. Whenever I took organic chemistry, I struggled so much with definitions of polar or nonpolar. I was like, that thing with the oxygen, I think I can call that nonpolar. Why? Because non has an O in it. I struggled with that a lot. Now, whenever I put it in the context of electronegativity, that's helpful because then I can kind of visualize the periodic table and think, okay, the most electronegative element is fluorine. Well, oxygen is pretty darn close to fluorine. So oxygen, given the opportunity, it's pulling electrons away from something else. So whenever I see something like this right here, a carbonyl carbon and a carbonyl oxygen, got news for you. Well, this one right here is going to have a partial positive charge. This oxygen, with it having two lone pairs of electrons, that's going to have that partial negative charge. So that's really helpful for me. Now, we typically are going to classify our intramolecular or our covalent bonds as being polar covalent, something like this right here up at the top. Then in the middle, we'll have our nonpolar covalent, where these black dots represent individual atoms or nuclei. And in our nonpolar covalent, we've got atoms, or sorry, our electrons are being shared equally, whereas our polar covalent, they're being shared, but this one on the right here really has those electrons more. Now, I think that if you remember this right here, that's going to be helpful for understanding peptide bonds and thinking about peptide bonds and their charge disparity. And it's going to be helpful later on when we talk about sugars. Now, the last example when we talk about a type of bond is, well, we talk about ionic bonds, where we have basically an extreme version of a polar covalent bond, where one species, and this lowest model here, this red, or sorry, this purple atom has completely given up an electron. It gave it away, and our green atom accepted those electrons. So we have defined separate charges. Okay, if you can work through that and understand kind of that range there, you're going to be in good shape. What I would commit to memory most here is the examples of a polar covalent bond and an ionic bond, because polar covalent are going to be helpful for understanding peptide bonds and charges of peptide bonds, whereas ionic bonds are going to be helpful for R group interactions. So I'll say R groups here. And then up here, we would have peptide bond. Now, our peptide bonds being examples of polar covalent bonds, well, whenever we see, what is this little this cobra snake look like right there? What does that indicate? Next to the minus or next to the positive. Add that to the chat. Partial. Now, by it meaning partial, does that mean complete? I am kind of being snarky with that question. Exactly. No, it doesn't. It means partial. You're absolutely right. So whenever you see a partial charge, you indicate it. You don't say, "Oh, well that's a partial negative," which is effectively a negative. So what that means is when we see something like a peptide bond right here, is that right there charged? It's got a partial charge. It doesn't have an overall charge. So this oxygen has lone pairs of electrons, and you'd give it that partial negative in this partial positive, but it's not going to have a full-on negative charge. And one important thing to remember moving forward is that a peptide bond never has a full-on charge. That's an important detail because whenever it comes to calculating a charge of a peptide or something like that, you do not need to account for the peptide and say, oh, well, based on the pH, the peptide would have a positive charge. It will not. The peptide will also not have a negative charge depending on the pH. So you don't have to worry about, groups that are involved in a peptide bond contributing to the overall charge or ionization state of a molecule. Okay, next up. And actually, can I get a thumbs up or yes added to the chat if you're good on this? Okay, or in the video. Okay, cool. And if this is something that you want more to discuss more, I'm more than happy to. I just want to kind of get a catch-all here. Okay, cool. Now, next up, bonding review part 2. This is really dealing more with our intermolecular forces. Now, our intermolecular forces, we've got bonding between two molecules. And if you look in the lower left-hand corner, we've got a spectrum ranging from our weakest intermolecular forces to our strongest intermolecular forces. Our strongest intermolecular forces, right up here. Ion-ion, a cation and an anion. The strength with which they can be held together ranges from 400 to 4,000, and this is kilojoules per mole. If you have any memory of, well, what's a covalent bond strength? A covalent bond can be as strong as that. If we talk about a carbon-carbon bond, if we talk about a carbon-carbon like triple bond or a double bond, it might be as strong as that. They can be extremely strong, but I would look at them almost as strong as close to as strong as a covalent bond. Now, what we also have is kind of a second class of our intermolecular forces. We've got ion dipole, so something with a full-on charge interacting with something that has a partial charge. So sodium ion and the oxygen of a water molecule. So the sodium ion has a positive charge and the oxygen has a partial charge. Those are, well, potentially strong, but they're weaker than that. Then we've got hydrogen bonds. When we talk about a hydrogen, or a hydrogen bond, we have to have a hydrogen, and then nitrogen, oxygen, or fluorine. Those range from 10 to 40 kilojoules per mole, so they're about at best, they're 10 times as weak as a ion-ion bond. Then we've got dipole-dipole interactions where they're weaker than our hydrogen bonds typically. And then last but not least, we've got our dispersion forces. So our London dispersion forces, or our LDF, or our induced dipoles. Those are weak. So we've got all of these, and I think what's most important is to keep in mind what we'll be talking about a lot here are these hydrogen-hydrogen bonds, because they can be strong, especially when you've got numbers. And those in particular are strong when we look at and explore the next level of protein structure. Our next level of protein structure after our primary structure is known as the secondary structure. These are often referred to as local structures, and these are stabilized by hydrogen bonding, where an amide hydrogen and a carbonyl oxygen will hydrogen bond with one another. So the hydrogen that is bound to a nitrogen and an oxygen, which is bound to a carbon, we've got our oxygen going to a hydrogen going to a nitrogen. With these secondary structures, we're going to have, we're absolutely going to have some patterns. The secondary structure of a protein can be predicted, and we'll get into that a little bit later today. Your amino acid side chains, or your R groups, the identity of the R groups is not super important, but it's not something that can be completely ignored. The R group identity is really important when we get to our tertiary structure. We're going to come back to secondary structure in just a moment, but what we see here, this is an alpha helix, and this is a beta sheet. Okay, so these are our two major structures for our secondary structure of a protein. Our third level, our tertiary structure, is formed by a single polypeptide. This is an important detail, a single polypeptide. This is stabilized by covalent and intermolecular forces, but this is between R groups. So the amino acid identity is important for the formation of the tertiary structure. Now, I always kind of think about tertiary structure as, well, it is built on the foundation of the forces that stabilize your primary and your secondary structure. But in terms of actually folding into that 3D shape, we're just interested in those R groups. Does that mean you can break all the peptide bonds and, oh, tertiary structure still exists? Not at all. That just means that what we're most interested in when it comes to tertiary structure is those R group interactions. And so this is where we are interested in hydrogen bonding. We're interested in dispersion forces that lead to the hydrophobic effect, and then electrostatic interactions like ionic interactions and dipole ion interactions. That's where we're kind of interested in those. So that's why it's important to know what an amino acid R group looks like and to be able to classify something and say, oh, well, tryptophan, that's a pretty non-polar group, so it's probably not going to establish a uh, ionic interaction with anything. That's why that sort of thing is important. Does that make sense? Okay, so we'll go forward. And like I said, we care about, or when it comes to tertiary structure, we're thinking about the foundation, the primary and secondary that led to this. Our fourth level of protein structure is our quaternary structure. This is formed by two or more peptides. There is a protein, and I'm going to give you a little bit of a hint as to its name and add it to the chat. It starts with an H, and this is what is commonly known as a tetramer. And I'm going to start spelling out the name, and then people are going to add it. H-E-M. Hemoglobin. You're absolutely right. I know. This is why I play trivia and do not like lead trivia games. So that I'd be like, I'm thinking of a movie. It starts with a T. That's right, the Maltese Falcon. Hemoglobin. So hemoglobin is an essential protein for great, taking oxygen from our lungs and transporting it through our body. We're going to study hemoglobin as kind of a model for quaternary structure and function of proteins. But hemoglobin is a tetramer, and it's made up of four different subunits. So these individual subunits, they kind of fold together. Here's one, here's the other, here's the other, and here's the other. They fold together, and when they fold together as that tetrameric unit, then they're functional. Individually, like if we extracted this one away and we're like, okay, go to town, that singular protein is going to be like, I can't do anything. So a quaternary structure of a protein is where multiple polypeptides fold together and do something. Quaternary structures can assemble and disassemble transiently, and the assembly and organization influences the function. We're going to get into quaternary and tertiary structure more in depth on Wednesday. I know that I spent a chunk of time on kind of foundation, but now we're jumping into secondary structure even deeper. Okay, so here what we have is a simple polypeptide. Now, whenever I say simple, I just mean it's just got a couple of amino acids. What I want you to notice whenever you look at a peptide like this is I want you to try to dissect and figure out a few things. What I think is most helpful whenever I see a model like this is I want to figure out where my peptide bond is or my peptide bonds are. I want to figure out where my N termini is and my C termini. Okay, so if I look over here, my free alpha amine, I notice that it's protonated. Okay. Does that information, what information do I have based on it being protonated? Well, it'll take me a minute to think about that. Then I'm going to go over to my C termini. I see that that's deprotonated. Okay. Now, just as a general rule of thumb, your N termini of your amino group, your N termini of an amino acid is going to have a pKa of about 9. Now, I'm never going to ask you to memorize pKa values. I'm going to give you pKa values on your exam. And anyone who asks you to memorize pKa values needs a hobby. Now, with that in mind, let's look at approximately the pKa of our C termini. That's about 2.5. So we got about 2.5 and 9. Now, based on that, now I'm not going to look at the individual R groups. We'll do that in just a second. But based on this, what can we say about the pH of the solution that this peptide is in? Only based on those two data points. And go ahead and add. You can put a number in. Okay, got to vote for it's below 9. I support that. Perfect. It's above 2.5 and it's below 9. That's a great piece of problem solving that you've come in with, where you've analyzed those two groups. And I know that if my pH is 7, we'll say, well, then I have a decent sense of how many protons and how many, well, Brianna, that's a great question. That's where we would calculate our PI if we had those two. So I like where you're going with this. But if we're going on just those two data points, and this were the question, what is the pH? Now, a short answer question, yeah. If somebody said, oh, it's 4.6, okay, that's above 2.5 and it's below 9. If someone said 8.9, they would be just as right as the person who said 4.6. Because what we're interested in is what this molecule or what the pH of the solution that this molecule is in. And based on the acidic group, this 2.5 being deprotonated, and this basic group being protonated, well, we know that it's the pH is, or the solution of our pH is more acidic than this group right here. Okay, now that's the first thing that I want to do. And I think that's really a helpful thing to do. And this is just kind of analysis of these groups because I want to show you a web page in just a second. The next part of this group is, or the next part of the analysis of a molecule like this is you find your peptide bond, okay? The way that I think about it, the backbone of a polypeptide is I think NCC, peptide, NCC, peptide, NCC. And so every time I list my second C, what follows is that pattern of NCC. And so I'm saying NCC, peptide bond, NCC, peptide bond. And that's helpful for me. After that, what I'm going to do is I'm going to look back and think, okay, what else do I know about a peptide backbone? What I know is I've got my N and then my alpha carbon. And off of my alpha carbon is where I'm going to find my R group. So the first one, I've got a hydrogen, which comes off of my alpha carbon, and then I've got another hydrogen. Well, That means I have two hydrogens coming off of one alpha carbon, which is the amino acid glycine. Now, it gets a little bit easier whenever you see things like a bulky group like this, a phenylalanine or something like that. Now, I have to open a browser window real quick, and I'm going to share this with you, in part because um, I have a handful of tattoos on my person, and that's not completely relevant to this class. But in the event that you're like, I need a tattoo and I don't know what to get. Well, this web page that I'm about to share with you is going to be one where you're like, done, got it. This web page is none other than, find the share tool, pepdraw.com. So this is my second bit of product placement in the day. What this tool is useful for is I think that it's very useful for a couple of different things. One of which is understanding and kind of drawing out what does an amino acid look like at a particular pH. So what we can do is we can look at these amino acids. I'm going to add the URL to the chat. So boom, there you go. Oh, no, that was supposed to get everyone. Boom, there you go. What you can do is construct a peptide. I have a couple of children, and one of my children's name is Walter. And if Walter were a peptide, the W, the tryptophan, would be my N-terminal amino acid. The R or the arginine would be my C-terminal amino acid. So if I wanted to get a tattoo of Walter's name as a peptide at a pH of 7, this is what it would look like. Now, if I wanted to say, well, yeah, but sometimes Walter's a little spicy and he's like a little acidic, so I'm going to go with how about his name at a pH of 1? What would it look like? Boom. Oh, my C termini has been protonated. Toggling back and forth between those things, I think, is particularly helpful because you could also, if you're, you know, just getting into like studying your amino acids and thinking about their ionization. Let's start with alanine. Draw that peptide. Done. Okay, now let's see alanine at a pH of 3. Let's go with 4. I'm guessing, this one of the shortcomings of this webpage is it doesn't have my pKa values defined. But I know that my R group, or sorry, my C termini of this amino acid is probably going to be deprotonated at a pH of 4 because my C termini has probably a pKa of about, 2 or so. Draw peptide. Done. If I went up to 11, what does the predominant form of this look like? Well, done. In addition to that, this can calculate your isoelectric point of that peptide as well as the net charge of at that particular pH. Now, one thing that I want you to notice, and we talked about this a little bit, but I want to bring this detail back, as the isoelectric point is a unique property based on the pKa's. You're never going to say, oh, well, the isoelectric point of this molecule changed now that it's in a pH or a solution with a pH of 11. Look at the isoelectric point here as I change my pH to 3. Still 5.61. Does the charge of my molecule change? My molecule's charge does change, but my isoelectric point does not. Okay, so I think this is a really helpful tool for learning and getting more comfortable with your amino acids. So awkward. Peptide, done. Want to get that tattooed and then awkwardly bring that up in conversation. Hey, would you like to see my awkward tattoo? And then you show people that. And then they're like, I don't get it. And then some biochemist or cell biologist in the bunch is going to be like, haha, I see it. Perfect. Anyway, I wanted to share that URL because I think that it's really helpful. And, tattoo ideas. Okay, so now this is our structure. This is our general overview of this molecule. It's going to change its ionization state based on the pH. Now, the peptide bond itself, let's dissect those individual peptide bonds. This is a carbon to nitrogen bond. It is going to be resonance stabilized. That I said that it would never have a charge, and I stand by that. I stand by that because of the fact that, well, in one resonance structure, it will have a charge, but that's just a snapshot of that bond in a fraction of time. That's a snapshot. That's not what it exists as. It's going to be resonance stabilized. So you're going to see this model that's shown on the left here. The single bond is what you're going to see between the carbon and the nitrogen. It's important to know that it is resonance stabilized because what that tells you is that the peptide bond, by it being resonance stabilized, has about 60% double bond property or double bond character. So it's shorter than a single bond, but longer than a double bond. Now, what that also means, and what's really important for this, is that it's rigid and very inflexible. So you're not going to have a lot of rotation in terms of the groups that are basically adjacent to that. Now, that's a little bit complicated because we were talking a little bit about the tertiary structure of a protein, something folding in 3D space. Well, how do we fold in 3D space if we have these, every two bonds, we have something that's super strict and rigid? Well, we have that because the bonds adjacent to the peptide bond that I circled here and here, those that flank the peptide bond, they still have some mobility. Those can still rotate. Now, those will contribute ultimately to what a protein looks in 3D space. Now, this right here, this plot is known as a Ramachandran plot. So this plot right here is a Ramachandran plot. And what this shows us are bond angles of the bonds that are adjacent to your peptide bond. So I'm going to give you a linear N, C, C, N, C, C. I'm going to scroll that out. Now, the first thing that I'm going to do is I am going to switch to my highlighter and highlight my peptide bond. That's my peptide bond. That's rigid. There's no rotation there. Now, what I also have here is the nitrogen to my alpha carbon. I have some rotation about this bond. This is known as the phi, or the rotation of this bond is known as the phi angle. That's denoted on the x-axis down here. So the way that I think about this, and I hope that you can follow me here, is imagine my hand here as being the basically a peptide bond. Is it okay to say that, Ollie? Yes, isoelectric points do not change when pH changes. That's fine. Okay, so imagine that my hand, and I've got a pen, wish I had a Sharpie, go with an N and then a C. NC, okay? Now, this portion of my hand is not going to rotate. I tell you, if this part of my hand rotated and this did not, I would be screaming. That would hurt. So my hand is not going to rotate. Now, I've got another peptide bond here. And here's what I've got, or I've got my other hand where, let's say that the tip of my middle finger is going to this nitrogen. This is, sorry. My hands are my peptide bonds. They're not going to rotate. What connects my hands, that will rotate. That's my phi and psi angle. Now, these phi and psi angles, they can each individually rotate, but they'll only rotate a certain angle. So let's say that If you look at my right hand, that rotates, and it has rotated where my palm is now facing the camera. This has gone, here's 90 degrees, here's 180. Okay. Now, if I go the other way, ugh, I'm not particularly flexible. I'm rotating this way. That's a negative 90-degree rotation. Is ever, can that, can anyone follow that? Okay. So we have these rotations. We have a phi angle bond rotation and a psi angle bond rotation. Just as it's painful for me to rotate my hands in certain combined directions, the same thing is true for a peptide bond. And so these shaded regions right here, these blue and light blue regions, illustrate the favorable bond angles that phi and psi angles can attain. So think about this as basically like a map almost of saying, okay, here's my phi angle. And so the this can rotate, let's say negative 120. And then this right here is my psi angle. If my phi angle goes negative 120, my psi angle could go, well, it's pretty much got to be positive. I'm going to say that's positive 120 degrees. So those are the combined bond angles that are favorable for this to take. Now, all of those bond angles are important for the stabilization of the secondary structure. Now, in my opinion, I hope you find this relatable. This is the most abstract part of secondary structure. This is tough to wrap your mind around. But just think about it in terms of in organic, you talk about like torsional strain and steric hindrance. This is all accounted for whenever we talk about the rotation of these angles. So the phi and psi angles are the ones that we're interested in. And the phi and psi angles correspond to the covalent bond that follows our nitrogen going to our alpha carbon, and the psi follows that. What's helpful for me is whenever I think of a polypeptide backbone, I think of NCC peptide, NCC, and so on. I also think phi, psi, peptide, phi, psi, peptide. So if you kind of keep that straight, that's going to be particularly helpful to you. Now, with that in mind, what we've got here is also an alpha helix. So an alpha helix and a beta sheet are the two bond angles that are kind of most important for, alpha helix and a beta sheet are the most important structures for understanding secondary structure. An alpha helix is stabilized by hydrogen bonds between the amide nitrogen and the carbonyl oxygen. This is considered a right-handed helix. Now, if you're ever thinking about, well, what's a right-handed helix? Essentially, what that means is you use your right hand, and the way that your palm folds in is the directionality of that peptide or of that polypeptide and how it kind of winds and wraps. Now, it's a cylinder shape. Different parts of the helix are above one another, and the height of one complete rotation is 5.4 angstroms. 5.4 angstroms. Now, each amino acid is approximately 1.5 angstroms. And whenever I say this is in all directions, I'm meaning, so here's my NCC. So that right there, it occupies 1.5 angstroms in the Y, X, and the Z plane. Now, with that in mind, one complete rotation. So one cylinder spin is about 3.6 angstroms. So it's 5.4 angstroms tall each rotation. And that's these are like the three detailed pieces of information. These are the three numbers that you need to remember about an alpha helix. The reason for that is it's going to be helpful when it comes to calculating basically the size of an alpha helix and the height that it could take. Now, an average alpha helix has approximately 10 amino acids. The hydrogen bonds are parallel to the helical axis. Your carbonyl oxygen is hydrogen bonded to the NH of the amino acid that's 4 amino acids away. So this is also termed the I to I plus 4. Now, if one of the ways to think about that is to put it in a linear sense. So I'm just going to draw boxes. These are representing my different amino acids. Amino acid number 1 is hydrogen bound to amino acid number 5. Amino acid number 2 is going to be hydrogen bound to number 6, 3 to number 7. And that image that I've got at the bottom there is translated to kind of winding around because I've given you the kind of linear model there at the bottom of the screen, but then that kind of winds up and gives you information based on kind of the stacking there. Now, what I think is a important to understand about this alpha helix is how to use that information. So, my first question for you that I'd like folks to respond with is how many amino acids are required for an alpha helix to span a 40 angstrom lipid bilayer? Okay, so just going to kind of give you a visual here. Here's our lipid bilayer. This is 40, and then I'll always love drawing the symbol for angstrom, 40 angstroms. So keeping in mind or taking into consideration that, well, one complete rotation is 5.4 angstroms, and that one rotation requires about 3.6 amino acids. Those are the two pieces of information that you need for this. So I'll go ahead and put that down here. One rotation, or one rot, is 5.4 tall. Absolutely. So one rotation is 5.4 angstroms tall. One rotation requires 3.6 amino acids. Okay, so repeated the question. How many amino acids are required for an alpha helix to span a 40 angstrom lipid bilayer? I got a response of 26.7. 27. Okay. Now, if you want to set this up, I think that you guys are all coming up with the right answer. If you want to set this up as a dimensional analysis problem, which I got to be honest, I've taught Gen Chem 1 enough that I really like to. So 40 angstroms, that's my goal. I've got a 5.4 angstrom tall with one rotation. On the exams, you'll see questions like this. How many rotations are required to span 40 angstroms? And so if that was the question, you would stop right here. But what if I'm asking how many amino acids, then I'm going to say one rotation. Each rotation is 3.6 angstroms, or 3.6 amino acids. Well, then I'm going to do 40 times 3.6 divided by 5.4. And it seems like everyone's rounding at about 26.7. I think 26.7 or rounding it up to 27. I'm going to go ahead and trust the consensus's calculations there. So that's one of the ways that I'm going to ask this sort of question. And essentially what this means in terms of sig figs, I'm not going to lose any sleep over that. The way that I like to answer the way that I like to phrase this question on an exam is I like to say, how many complete rotations will this require? And so then your answer would be 27. because I'm defining, well, it's not going to be done with 26 complete rotations. It needs 26.7. 0.7 is not a complete rotation, so I'm going to round it up to 27. Now, next question. How tall or long is an alpha helix with 110 amino acids? Okay, I'm going to clear the writing on this one. Actually, I'm not going to clear all of it. Got answers rolling in. Knew it. Knew it. I knew it. I asked you guys a question. I knew you'd just be like, done, 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 done. Well, how tall is this? 110 amino acids. Drawing a relationship here. 3.6 amino acids is one rotation. One rotation is 5.4 angstroms. 110 times 5.4 divided by 3.6. Dunzo. I think it's, yeah, I feel comfortable with 165. Then, how many amino acids are required for an alpha helix to have 3 complete rotations? Okay, so one rotation is 3.6 AA, approximately. We'll want to multiply this by 3. Well, that would be, let's see, 1.229. Yeah, it'd be about 11 is what I'm looking for there. Okay. So that's one of the ways that we use this alpha helix information. We want to figure out basically how tall one rotation of an alpha helix is, how many amino acids are required to make that complete rotation. And if you're having any issue visualizing what I mean whenever I say a complete rotation, I'm going to use this piece of a USB-C cable that I have. Let's imagine that this box cutter that I have is an axis. Okay. I've got my USB-C port right here, and I'm wrapping it around. And from here, where my thumb is, to here, where my index finger is, that's one complete rotation. So if I were to wrap this around here, now I've got 2 complete rotations. This USB-C cable isn't long enough for anything more than that number of rotations. So it's basically like where you complete it. If you think back to like sinusoidal waves from like a trig class or something like that, where you have the beginning to the end to make one complete wavelength. Okay, so that's important information when it comes to an alpha helix. Next up is what's a model known as a helical wheel, or the helical wheel. Now, this is a very valuable tool for visualizing where different amino acid R groups are and where they end up on an alpha helix. This shows the relative positioning of each R group with respect to one another. Now, this is important to see, basically translating from a linear polypeptide to what these amino acids look like on a kind of 3D scale. So the important part about this is when you look at a linear model of a polypeptide, what amino acid is right next to amino acid number 1? Add it to the chat. The amino acid, sorry, I meant in my linear model. 1, 2, 3, 4. Sorry, I apologize. Yeah, I'm looking for number 2. Number 2 is right next to it. You guys had the answer kind of where I was going though, of well, whenever this helix has formed, what is right next to amino acid number 1? Well, it's going to be 5, and then 8, and then 12. The identity of those amino acids. For instance, if number 1 is a polar residue and 5 is a polar residue, and let's say 12 and 8 are all polar residues, that means this side of my peptide, it's going to have a dense packaging of polar amino acids. So what do you think those polar amino acids are going to really want to do? they're going to really want to interact with other polar amino acids. Now, this shows the relative positioning of our R groups with respect to one another. And this is important for seeing where different R groups are so that how multiple helices can interact. So if you have, to kind of illustrate that, if we've got a helix that all of these are polar residues, that portion of that alpha helix is going to want to interact with another alpha helix that has a similar clustering of polar residues. Okay, so when it comes to the alpha helix, there's the math that's important, the organization of different amino acids that's important, the height, the dimensions there. Now, when it comes to a beta sheet, there's a couple of different variables that are important for beta sheets. First and foremost is, well, beta sheets and alpha helices are stabilized by the same force, hydrogen bonds. Now, looking at these two models, on the left-hand side, we have a, well, we have kind of a rotation there about those, but, um, sorry, just a second. Something's going haywire. Um, we've got kind of rotations and angles that these different um, beta sheets can take on. And so, although they have, kind of a seemingly rigid structure, on the right-hand side, you see basically how they look in terms of where all those atoms are. And I've got a poll question for you, and I'm going to have more poll questions next time, but which one of these, my stronger is basically, or my question is stronger. I know that a single word usually does not make an entire question, but which of these two do you think is stronger, the parallel or the anti-parallel beta sheet? And I'll give a little bit more time for, I'll give about 40 seconds on this, so about 15 more. Okay, I'm going to just leave this one open as everyone kind of files in with their answer. For those of you who are voting or voted in favor of the anti-parallel hydrogen bond, you are correct. Anti-parallel hydrogen bonds within a beta sheet or an anti-parallel beta sheet is stronger than a parallel beta sheet. And the reason for that is, I like that response. Looks more stable. You're right. Well, one thing about them, and what I think is kind of helpful to, visualize is these groups, and I know that I changed slide. These two groups right here are directly across from one another. You've got that hydrogen bonding connecting the two of them. Those two groups are directly across from one another, so there's no like angle that is influencing that causes that length to extend a little bit. Parallel and anti-parallel beta sheets have different strengths and differ in their stabilities, and they can organize in a number of different complex ways. Now, one way that they can get very complicated is with the help of, or they can form higher order structures known as beta barrels. Um, and basically, your anti-parallel beta sheets are strongest. Your alpha helices, your beta sheets, those are your two major secondary structures. Now, I haven't gone into and won't go into a huge amount about beta sheets because they're kind of boring right now. We'll get into them more when we talk about like membrane proteins. Now, there are other secondary structures. There's a reverse turn, there's a beta turn. Um, these are kind of these are like let's see, they're like the guy who was Nirvana's drummer before Dave Grohl. His name was Chad Channing. Nobody really remembers Chad Channing. It was then, yeah, he just wasn't there. These are relevant, they contribute, but they're kind of spectators almost. Now, what's so important about secondary structure is that secondary structure can be predicted. And I say it can be predicted And what I mean is with a high amount of certainty and with a high amount of um with certainty and with confidence. That's the word I was looking for. So if you look at this chart on the left-hand side, we've got a list with our amino acids, three-letter codes, alpha helix, beta strand, reverse turn. And then we've got numbers. These numbers range from basically 0 to 2. And these are what are known as propensity scores. And it was back in, I think it was 1978 or maybe 1976, that two researchers, what they did was they read through all of the literature of the day and they said, okay, of all the protein structures that have been solved, let's score every single amino acid. Let's look at how often an alanine is found in an alpha helix or a beta sheet or a reverse turn. Let's score every single amino acid. And then we're going to publish this as, hey, every amino acid has been scored, and here's the likelihood that this amino acid is going to be found in this particular structure. So the value of this is now all of a sudden people could take a primary structure and say, okay, based on the primary structure, I'm guessing there's an alpha helix that forms here. And it's 32 amino acids. So it's probably these rotations. So rather than looking at a protein and saying, oh, okay, well, here's the protein structure, instead, what they would be able to do is say, I'm going to predict that my protein looks a little bit like this. And that might seem insignificant, but that's a big step forward. And it's a big step forward because if you have an idea of what the secondary structure is, then you have some ground to stand on for predicting the tertiary structure. And if you're at all familiar with AlphaFold, that's a piece of software that basically enables someone to plug in a protein structure and predict what it looks like in 3D. And that's very powerful because that gives you a mechanism to be like, that crevice right there, I think that's where I could design a drug to basically knock out the function of that protein. So understanding tertiary structure or quaternary structure is extremely powerful. But that's standing on the shoulders of the giants of understanding secondary structure. Now, the take home, I don't want you to commit these to memory. I do want you to know names. From time to time this semester, we'll talk about names. Chow and Fassman were the people who put together this review article. It's the Chow-Fassman prediction model. Now, there were some details. The cool thing about this is an ever-evolving scoring scheme. So they identify, I think the general trends still remain the same, and nothing's radically changed, but basically that's kind of what they got. In terms of most residues most likely to be found in different structures. Now, as a general rule, what I want you to know about individual amino acids is that an alpha helix is going to prefer smaller and less bulky amino acids. You're more likely to find an alanine, glutamic acid, a methionine, leucine, or a phenylalanine. You're less likely to find a proline, a histidine, an arginine, or a glycine. Now, in a beta sheet, your preference is to find, or what's more likely to be found, are large and bulky residues. Tyrosine, tryptophan, phenylalanine, methionine, isoleucine, valine, threonine, and cysteine. Those are likely to be found there. You're less likely to find proline and glycine. And I want to highlight those two because they are what are considered secondary structure breakers. And they are breakers for the exact opposite reasons. I thought I heard something, but I apologize. A proline is considered a secondary structure breaker because it's too rigid. So in both cases. And if you think about the amino acid proline, what does that R group look like? The R group goes back to the N-termini. Glycine is too flexible. So they basically disrupt for opposite reasons, but they have the same effect. Then the last thing with respect to protein structure, I know it's 7:50, so we are effectively done. There's tons of different pieces of software that you can use to predict secondary structure. This is not something that you're going to be doing by looking at individual amino acids. There are certain residues that are favored in an alpha helix, certain that are favored in a beta sheet, and then others, proline and glycine, that disrupt them. Hydrogen bonding is something that's favorable when you have that I to I plus 4 of the backbone. What I want you to take away with respect to secondary structure and individual amino acids is glycine and proline, they're going to disrupt the secondary structure, and that's your takeaway. And then I also want you to be able to, you know, this seems like a very low-hanging fruit, but understand that propensity score. Like if we look at, say, let's go with isoleucine. Isoleucine could be found in a beta strand. It could also be found in an alpha helix because it has a propensity score of greater than 1. Where is it more likely to be found? In beta strand, because it has a higher propensity score. That's the kind of critical thinking question that I want you to be able to answer. Okay, guys, I sincerely apologize. It took more time than you were very gracious in letting me have this time. I'm going to go ahead and stop my recording. I'll hang around for a minute if anyone has